Hello, I'm Seema and welcome to part 14 of the chapter Solutions. In part 13, I discussed ideal and non-ideal solutions. By mistake on the board, I had written 12 and I did not change it. So on the board, it's written as 12, although I've uploaded that video as video number 13. I'm sure if you look at the list, the playlist for this chapter, you will find it as video 13. So I told you about ideal and non-ideal solutions. Ideal solutions are those binary solutions which obey Raoult's law under all concentrations. That is, whatever is the mole fraction, they always obey Raoult's law or almost nearly obey Raoult's law. And ideal solutions are very rare, and there are very few solutions which may which may be almost ideal, although absolutely ideal solutions do not exist. And the other kind were the non-ideal solutions. What were non-ideal solutions? They were the solutions that showed positive deviation or negative deviation from Raoult's law. In Raoult's law, we plot a curve between the vapor pressure and the mole fraction of the components, and we get a straight line for the total vapor pressure, as you see it here. The vapor pressure of one component, vapor pressure of the other component is shown like this, and the total vapor pressure, it usually follows the straight line. Now, for non-ideal solutions, these solutions show deviation from that line. They either are more, they show vapor pressure higher than that, or they show vapor pressure lower than that. And the reason for that, I had explained to you that if the forces of attraction between the dissimilar molecules, that is the molecules of the solute and solvent, the forces of attraction, their forces of attraction may be different from the forces of attraction of the constituent particles among themselves. That is, if you have only the solvent molecules, the attraction or repulsion between solvent molecules when they were not mixed, and the solvent molecules when they were not mixed. And after mixing them, the interaction between the two molecules, that is A and B, when they interact, the forces of interaction when they are different, at that time the solution shows a deviation from Raoult's law. In order to revise that, I would encourage you to view the previous video and then come to this, because this is now a specific situation of that positive or negative deviation. So in this video, I'm going to tell you about azeotropes. When I talked about that positive and negative deviation, when you have such examples where there is a large positive deviation or a large negative deviation from Raoult's law, such solutions, they tend to have a very characteristic, they come in a very strange situation. And the situation is that when they show the positive or the negative deviation, there comes a point when the deviation, the positive deviation is maximum. And there comes a point similarly for a minimum, for a negative deviation example, that there comes a point where there is a minimum point. Now, whatever this point, whatever this maximum or minimum is, like here there's a maximum, you see here you see a minimum in the vapor pressure, so it's showing this is showing a negative deviation, this is showing a positive deviation. So when they show that point where it is maximum or minimum, whatever is the concentration of that solution at that point, that is a concentration at which there is maximum deviation from Raoult's law. Whether it is the maximum point or the minimum point, whether the deviation is positive or negative. But what happens at this point is that at this particular concentration, where the mole fractions of both the components, they become fixed in both the liquid state and the vapor state. At this point, the concentrations of both of the concentrations of the components in the liquid state and in the vapor state, they become equal. And when they become equal, the entire mixture starts boiling at a particular boiling point. So they kind of get a common, one particular boiling point. A constant boiling mixture, we call it. It turns into a constant boiling mixture, which means that both the components start boiling at a constant temperature, right? Now, this is a very unique situation. When both the components start boiling together, do you remember you had studied about fractional distillation of petroleum in lower classes? What do we do in fractional distillation of petroleum? when we get petroleum from the earth, the various components of petroleum, they have different boiling point ranges. So we vaporize the entire petroleum and the vapors start rising, and as the temperature lowers of the rising vapors, the fractions are separated, they liquefy and they are distilled out. And when they are distilled out, every fraction it separates out with distillation. Now in the case of such a mixture, when you have the mixture of components that are boiling at the same temperature, do you think it would be possible to separate those components by distillation? By fractional distillation? No. So this forms a specific kind of a mixture or a solution which is constant boiling. It has the highest or the lowest vapor pressure, and its composition in the liquid and the vapor state have become constant, and it cannot be separated by fractional distillation. And since it has such unique properties, the mixture at such a point was known as an azeotrope. So what are azeotropes? Let us start studying about it. Azeotropes are binary mixtures. Binary means mixtures of two components, one solute and one solvent. They are binary mixtures having the same composition in the liquid and the vapor phase, and they boil at a constant temperature. Now, when they boil at a constant temperature, they cannot be separated by fractional distillation. That is the consequence of it. That since they are boiling at the same temperature, it is not possible to separate them. And that is the reason why when you have alcohol cannot be separated by fractional distillation. The maximum purity of alcohol that you can obtain aqueous, that is from its mixture in water, is 95% alcohol, ethanol. It cannot be separated. You cannot separate. At least 5% of water is going to be there in it no matter what, even at fractional distillation. Why? Because at that composition, ethanol in water will form an azeotropic mixture. And once the azeotropic mixture is formed, you cannot separate the components by fractional distillation. In order to separate that 95% ethanol from water, from that 5% of water, to get absolute alcohol, you will have to use the azeotropic distillation, which is not covered in our syllabus at this stage. But by fractional distillation, it is not possible to separate it out. So what are the main points that you need to remember about azeotropic mixtures? The first, that azeotropic mixtures are binary solutions. They have a fixed composition. Because this happens only at a certain composition. As I told you, in the case of ethanol in water, as long as the concentration of ethanol in water was different, it did not behave as an azeotrope. It behaved as an azeotrope only when the concentration reached 95% of ethanol and 5% of water. That is when it starts behaving as an azeotrope. So solutions behave as azeotropes only at fixed compositions. When they behave as azeotropes, they start boiling at a constant temperature. And at this point, fractional distillation is not possible. Why? Why is fractional distillation not possible? One, because both of them are boiling at the same temperature, so they would condense at the same temperature. And since the mole fraction in the liquid state, that is XA, is equal to YA, which is the mole fraction in the vapor state, then obviously all of the liquid is going to rise. How do we separate salt from water by distillation? We boil the water, and the boiling point of salt is a solid. So it would first turn into a liquid, then it will turn into a vapor. Much before that, the water vaporizes. And when the water vaporizes, you remove it, you condense it, and you remove it. But in the case of a mixture which is boiling at the same temperature, it will rise together. It will still, whatever was the composition in the liquid state will be the composition in the vapor state, and when you condense it, it will be the same composition in the condensed state or the liquid state. Therefore, you will not be able to separate the components. You will only boil it and then condense it and get it again. You'll get the same mixture back again. Now, when is it that fractional distillation is possible? Fractional distillation is only possible when the value of XA is not equal to YA. For example, you have a mixture of ethanol in water, And let us assume that the concentration of ethanol is, or the mole fraction of ethanol is 0.4. We know the sum of the mole fractions of all the components is 1. So if this is 0.4, this should be 1 minus 0.4, that is 0.6. This is the mole fraction of both the components in the liquid state. So what is the mole fraction of both of these components in the vapor state? Let us assume that it is 0.3 and 0.7. Now, the composition of both the components in the liquid state and the vapor state are different. For such a mixture, it is possible to separate it by fractional distillation. But if you had got the same composition in both the states, then it would not be possible to separate them with fractional distillation. Now let us go a little bit more into details of the azeotropic mixtures. I told you that azeotropic mixtures are formed from solutions which show negative deviation or positive deviation from Raoult's law, and a large negative or a large positive deviation. And that point at which that deviation is maximum, at that point you will get the azeotropic mixture. So what are the type of solutions that could form azeotropic mixtures? Those mixtures those solutions which show positive and negative deviation from Raoult's law. So on the basis of this, you get two types of azeotropes: the minimum boiling azeotropes and the maximum boiling azeotropes. You remember, I told you in the previous video that vapor pressure is directly related to the boiling point of a substance. The higher the vapor pressure, it means that the liquid easily turns into vapors, and the forces of attraction between the molecules is not strong enough, and therefore it is easy for the molecules to vaporize. So they will boil at a lower temperature. But if the forces of attraction between the molecules is stronger, then you need to give more heat in order to break that, or for the molecules to overcome that attraction and escape as vapors. Therefore, those substances which have a low vapor pressure, they will have a high boiling point, and those substances which have a high vapor pressure will have a low boiling point. So those solutions which show positive and negative deviations will show two types of azeotropic mixtures: the minimum boiling azeotropes and the maximum boiling. That is, those azeotropes which have a minimum boiling point, and those which have a maximum boiling point. So solutions which show a large positive deviation from Raoult's law, they will have a minimum boiling point. Large deviation, which means positive deviation, it means vapor pressure is much higher. If vapor pressure is much higher, then the boiling point would be much lower, because they are the higher the vapor pressure, lower is the boiling point. So such solutions will form minimum boiling azeotropes, which means azeotropes which have the minimum boiling point. Why would they have minimum boiling point? Because the attractions between the components of the solution, that is A and B, solute and solvent, those attractions are less than the attractions between the components. If the attractions are less, then the vapor pressure would be higher. If the vapor pressure will be higher, then the boiling point would be lower. Now here are graphs that are plotted for an azeotropic mixture of ethanol. I told you that 95% ethanol, aqueous solution of ethanol, acts as an azeotrope. And let us see what happens at this composition. A mixture of ethanol and water, it shows positive deviation from Raoult's law. So since it shows positive deviation from Raoult's law, we plot this curve. It is showing positive deviation. And we find that although it is not following the line that you would expect, the total, P total, vapor pressure total, is higher. So it is showing a positive deviation throughout. But at 95%, here you have ethanol is 1 and water is 0. And here water is 1, the mole fraction of water is 1 and ethanol is 0. It means mole fraction of ethanol goes on increasing. So it increases, if you talk in terms of percentage, this is 100%, this is 0% of ethanol. So here, somewhere here, let us say it is 95%. At 95%, we notice that the vapor pressure of this mixture was highest. It was showing maximum deviation at 95%. At this point, it started behaving as an azeotrope, which means it started boiling constantly. Both the components started boiling together in the same ratio or in the same mole fraction, and the mole fraction in the liquid and the vapor state became equal, and it formed, that's called a constant boiling mixture. Now this constant boiling mixture is also a minimum boiling mixture. Why? Because highest vapor pressure would be minimum boiling point. So if we plot a graph now between the boiling points of the components and the mixture, what do we find? The boiling point of ethanol is 78.37 degrees Celsius, and the boiling point of water we know is 100 degrees Celsius. And when we get this constant boiling mixture or the azeotropic mixture at 95% of ethanol, at that concentration we find that if the vapor pressure was the highest, the boiling point is the lowest, and it's a constant boiling mixture, therefore it has a common boiling point. And that boiling point now is 78.15 degrees Celsius, which is lower than either of the components. This boiling point is lower than either of the components, and that is why it is called a minimum boiling azeotrope. It is called a minimum boiling azeotrope because it boils at a temperature which is lower than the boiling point of either of the components. And that is forming at, that means at 95% ethanol mixture, or at that composition, the boiling point reduces to 78.15 degrees Celsius. The other type of azeotropic mixtures are maximum boiling azeotropic mixtures. It is the opposite of the minimum boiling. This would be shown, the solutions which show large negative deviation from Raoult's law will form such kind of mixtures. An example of this kind is 68% of nitric acid. Also, if you talk in terms of interaction between the molecules, the interaction between the molecules of the solute and solvent, they are greater than the interaction between the molecules of the solute and solvent. And that is the reason why this negative deviation is shown. So this is a curve of where negative deviation is shown from Raoult's law. This was the P total that was expected, but we find that at 68% nitric acid, the vapor pressure turns out to be the minimum. And at this point, it starts behaving as an azeotrope. And correspondingly, if we plotted the boiling point of these components against the mole fraction, we find at the same composition, the boiling point is the highest. At that point where the vapor pressure was the lowest, naturally the boiling point would be the highest. Therefore P total would be the highest, and at that point it starts behaving as an azeotropic mixture, and therefore that becomes the boiling point for the mixture. So the boiling point of nitric acid is 83 degrees Celsius and the boiling point of water is 100 degrees Celsius, and when it starts boiling, due to the negative deviation from Raoult's law, it starts boiling at a temperature which is greater than either of the the solute and the solvent. So it boils at 125.5 degrees Celsius. Isn't this interesting? A very unique situation, at a very unique composition, these non-ideal solutions, they start behaving as azeotropic mixtures. And these azeotropic mixtures can be a help, and they can be a menace too. Because a menace, as I told you, that you cannot separate them by fractional distillation is a very simple process. All you have to do is boil. You're using heat to separate out components, but you cannot use that. So it becomes a menace in case of when you're trying to separate out, or you're trying to purify substances from their aqueous solutions or from their solution states. But it can be beneficial when you want the mixture not to be separated. In that state, making an azeotrope helps you. Now give me a moment. I'll tabulate a few examples of both minimum boiling and maximum boiling azeotropes. Now here are a few minimum boiling azeotropes and maximum boiling azeotropes, and I would like to go over them with you. Minimum boiling azeotropes, the first example is water and ethanol that we've done. The composition is 4.03% water and 95.97% ethanol acts as an azeotrope. The boiling point of water is 100 degrees Celsius and ethanol is 78.37 degrees Celsius, and what you need to pay attention when you're going to see all these examples is what is the boiling point of the mixture. The mixture is 78.15. Do you notice that 78.15 is less than both 100 degree and 78.37, which means that the mixture, the azeotrope, boils at a temperature which is lower than the boiling point of either of the components. The second example is water and pyridine, in the composition of 43% water and 57% pyridine. We know the boiling point of water is 100 degrees Celsius, pyridine is 115 degrees Celsius, and they boil when they form the azeotropic mixture. At this composition, they boil at 92.6 degrees Celsius, which is lower than both. Therefore, it forms a minimum boiling azeotrope. Ethanol and benzene also act as azeotropes at what composition? Ethanol is 32.4% and benzene is 67.6%. The boiling point is 78.37, this is 80.1 degrees Celsius, and the boiling point of the mixture is 67.8, which is lower than both. The fourth example is acetic acid and toluene. 28% acetic acid and 72% toluene act as minimum boiling azeotrope, where the boiling point of acetic acid is 118.1 degrees Celsius, toluene is 110.6 degrees Celsius, and the mixture, that is the azeotropic mixture, has a boiling point of 105.4 degrees Celsius. Coming to maximum boiling azeotropes now. The first example is water and nitric acid that I explained to you, in the composition of 68% nitric acid and 32% water. The boiling point of water is 100 degrees Celsius, nitric acid 83 degrees Celsius, and the boiling point of the azeotropic mixture is 125.5 degrees Celsius. Now, this is higher than either of the components, so it is a maximum boiling azeotropic mixture. Acetic acid and pyridine, in this concentration, that is 65% pyridine and 35% acetic acid, the boiling point of acetic acid is 118.1 degrees Celsius and pyridine is 115 degrees Celsius, and both of them, when they form the azeotropic mixture, the boiling point is 139 degrees Celsius, which is higher than either of the components. Then you come to chloroform and acetone. It is 80% chloroform, 20% acetone, acts as an azeotropic mixture, that is a maximum boiling azeotrope. The temperature of boiling point of chloroform is 61.2 degrees Celsius, acetone is 56 degrees Celsius, and they boil at 65 degrees Celsius when you form a mixture. So these were a few examples of both minimum boiling and maximum boiling azeotropes. And with this, I'll finish this topic right here. I hope you found it helpful. If you did, I would really be encouraged if you give me a thumbs up and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.